Hi. So far we talked about estimation methods for value at risk. So now we're going to start talking about estimation methods for the second risk measure, which is expected shortfall. All right. Once again, I'm gonna consider three sets of estimation methods. The first one is parametric. Parametric estimation methods. The second set is non-parametric estimation methods, and the third set is semi-parametric. Okay. So in this video, I will talk about parametric estimation methods for ES. Right? Alright, the first method, as before, is based on the normal distribution. So I shall assume that the losses, say, suppose the losses, say, x1 to xn are IID from a normal distribution with parameters mu and sigma squared. Okay. Now we know from one of the previous videos that the formula for expected shortfall when x follows the normal distribution is given by this. Right, and we also know, if you look at the video for the parametric estimation of VAR, that the MLEs, or maximum likelihood estimators for mu and sigma, are given by mu hat is the sample mean x bar, and sigma hat is the square root of this. Okay. All right. Hence, the MLE for expected shortfall is simply this one, with mu replaced by mu hat and sigma replaced by sigma hat. Okay. It can be shown, it can be shown that this estimator is asymptotically unbiased. And consistent. Right. You probably remember I defined these two terms, asymptotically unbiasedness and consistency, in one of the earlier videos. I mean, you should know this anyway from year 2 courses you've taken. Right. The next method I'm going to talk about is the uniform distribution method. Right. So I'm going to suppose that the losses x1 to xn are IID from a uniform distribution with parameters a and b. We know that for this distribution the formula for expected shortfall is a plus b by 2 times b minus a. And if you look at the video for parametric estimation of VAR, that you will see that the MLEs of A and B are given by the following. MLE of A is the minimum of x1 to xn, and the MLE for B is the max of the losses. All right. Hence, the MLE for expected shortfall is simply the following, with A replaced by A hat and B replaced by B hat. And once again, it can be shown, I would like you to try this when you have time, it can be shown that this estimator is asymptotically unbiased and consistent. Okay, so this is the second method. Now the third method is based on the power function distribution. So I shall suppose that the losses x1 to xn are IID with the cumulative distribution function given by this. Now, if you look at the video for the parametric estimation of VAR, you will see that the expression for VAR is equal to P to the power 1 over A. Right? I derived this in that video. Hence the expression for expected shortfall is 1 over P. Remember this formula. This is the formula for expected shortfall, which is 1 over P times the integral from 0 to P of T raised to the power 1 over A dt. Now, if you integrate this, you get okay. So this becomes, if you simplify this, you get P raised to the power 1 over A divided by 1 over A plus 1. So this is the expression for expected shortfall for the power function distribution. Right? Now, we also know that the MLE of A is given by this. So once again, if you look at the video for parametric estimation of VAR, you will see that I derived this. Okay, so this is the MLE for A. So hence, the MLE of expected shortfall is given by the following. Alright, so this completes method number 3. Now, the fourth and the final method is the Weibull distribution method. Right. So this is number 4. So I'm going to suppose that the losses x1 to xn are IID with the cumulative distribution function given by this. All right. Right. Now, if you look at the video for parametric estimation of VAR, you will see that I derived the following expression for VAR. right? So now I'm going to use this to derive the expression for expected shortfall. So the expected shortfall is 1 over p times the integral from 0 to p okay. You should sub this here, you will get okay. Now I'm going to make a substitution, right? So let me set y equal to minus log of 1 minus t, which implies that 1 minus t must be this, which implies that t must be this, which implies that dt by dy is e power minus y. So let me put this in a box. Right. Now subbing this back into the integrand, this is what you will get. You will get the integral equal to theta divided by p. The limits of integration will go from 0 to minus log of 1 minus p, and the integrand will become y raised to the power 1 over beta times e minus y dy. Now this kind of integral is known as the incomplete gamma function. You may recall that I defined the gamma function early on in the course. Now the difference here is that instead of going from 0 to infinity, you're integrating from 0 to a fixed number. And this kind of function is known as, right, let me write it down first. This is the notation I shall use. Right. Okay, and where this is the definition, is known as the upper incomplete gamma function. All right, so this is a special function that you may want to know. All right, so this here is the expression for expected shortfall for the y-wave distribution. All right, okay. Now let's see how we can estimate it. Now if you go back to the video on parametric estimation of var, you will see that the estimators of theta and beta, these are the two parameters that involve the variable distribution, are the solutions of the following equations. This is stuff I covered in the earlier video on parametric estimation of VAR. Right. So solutions of these two equations. Where x bar is the sample mean. So x bar is simply 1 over n times the sum of the losses. And S squared is the sample variance. So it is 1 over n minus 1 times the sum of the squares of the deviations. All right. So hence the estimator of expected shortfall is given by the following. So I'm just simply replacing theta by theta hat and beta by beta hat. All right, so this completes the Weibull distribution methods and also completes parametric estimation of expected shortfall. In the next video, I shall talk about non-parametric estimation of expected shortfall.